where are we? Come on. Come on, come on, come on, come on. There it is. Okay. So has anyone ever been to something like this? This is a picture from a club with kind of like a glow in the dark look. Or if you've been to glow in the dark golf or glow in the dark anything. This is mostly it's a purple light and blue light, but there's a little bit of what is called a black light. And so I happen to have a black light here in the house too. This is a black light that I'm going to use. I'm going to turn it on. And a black light is just that. It is a light that you can't see. Unlike visible light that's white, this black light you can't see. So I'm going to turn on this black light right here in my screen. And I've turned it on. And it looked black, and it still looks black, maybe a little bit of bluish purple. So it is the very low end of the visible light spectrum is violet. And just outside of that, just higher on that, the high end of the visible light spectrum, just higher than that is UV or ultraviolet. And so we get that violet blue light, but it's ultraviolet that we can't see. So this is not shining like a white light compared to this visible light. So here's a flashlight off and here's a flashlight on. And so you can see when I turn that light on, you have a light on compared to off. And this one is a little bit can be detected, but what we have that will really detect the UV is this will reflect off white surfaces. That's why it works in glow in the dark. But you have some beads. So there are different types of beads, and I'm going to switch to my camera, which is here. Switching to my camera, I've got different types of beads. These are standard colored beads. So standard colored beads don't respond to this black light, okay? And that gives a little bit of a purple glow on it. So those are standard colored beads. And then we've got these, which are glow in the dark beads. Let me see if I can find them. These are glow in the dark beads. And glow in the dark beads, they have kind of a whitish color. And there's a greenish glow to them under this black light, but they really only glow when you go into the dark. Okay, so this compares to UV sensitive beads. So these are UV sensitive beads that start off kind of a whitish color like the glow in the dark, but as they are exposed to this black light, okay, so putting this here, these beads that are UV sensitive beads start to turn different colors. You can see the glow in the dark beads are still just white, but these UV sensitive beads, which were kind of whitish, are now different colors. You can see they're pink and yellow and blue and purple, and it takes about 10 seconds. So it is a reaction that is a reversible reaction. So again, you've got the different types of beads, and these colored beads stay colored. They are colored. This is all the way over here, and the light does not change anything to them. Glow in the dark beads, they are whitish. This light doesn't change anything. But the UV sensitive beads are turning different colors because they're exposed to UV light. So now I just turned the UV light off, and that's that black light. Well, what happens is that this is a reversible reaction, and these beads, so going back through these again, the standard beads, they're just colored and nothing happens. They're still the same colors. The glow in the dark beads, they're still whitish, and the UV sensitive beads, in the absence of UV, turn back to this whitish, clearish look. So one is still pink, but it will take over time, these start to fade as colors. And so that's what you'll be looking at in these experiments today. I have some recorded videos for the experimental data, and also you will be doing at-home experiments with your own UV sensitive beads. So hopefully you also have these UV sensitive beads all ready to go and some materials to test. So those are the UV sensitive beads. So let's go back to here. So the idea of glow in the dark is really not glow in the dark. It is that there's a little bit of UV around in things like the black light that's used for UV sensitive inks. If you have higher denomination dollar or bills like 50s, 100s, there's UV sensitive ink on that. And a bank will use that UV sensitive ink that normal people cannot get. They'll use that to detect if it is a counterfeit or legitimate $50 or $100 or even $20 bill. Also on the California driver's license, there's UV sensitive ink for a mark on the driver's license, again, to detect if it is a counterfeit or fake ID compared to a government issued ID. And that's because the government can get a hold of and use UV inks, although regular people cannot. So I can't print it out on my computer with UV ink, okay? So it is used, the UV sensitive inks, UV sensitive beads, and it changes color in response to UV light, okay? So we know that even if you don't have a black light in the house, you can use sunlight as your source of UV. So sunlight contains UV as well as visible light and infrared. So that's UV or ultraviolet. And ultraviolet is on this end of the spectrum. And for the electromagnetic spectrum, this just shows a portion of it. Hold on a second. This just shows a portion of it. I need to get this back to where I was. Okay, this is the higher energy side. And this is the higher energy side that is the ionizing radiation. So this is the ionizing forms of radiation. And ionizing radiation can cause damage. So UV is the one that we are most exposed to because it comes from sunlight. And so that's why we have this. We're going to look into ways to protect yourself from UV, whether it's sunglasses or paying attention to UV index and a protection advisory. And that's mostly what we're exposed to as far as ionizing radiation. X-rays and also gamma rays, these are also higher energy. And for the most part, we are not exposed to X-rays and gamma rays. And the X-rays and gamma rays are basically, X-rays are a controlled amount. When you go to the doctors or dentists, they know exactly how much X-ray energy you've been exposed to. And you can only get certain X-rays like every other year, every 3 years. And gamma rays are a special case. If you're exposed to gamma rays, it's only because of a nuclear accident, which we'll be getting to into another module. So X-rays are really the other exposure in addition to UV. So everything below UV, so that includes visible light on down. So these guys, everything visible light on down, this is all non-ionizing radiation, and non-ionizing radiation does not do anything to you. It does not have enough energy. It is on the low energy side, and it does not have enough energy to break bonds in molecules or form ions. So this is infrared. That's heat that we've been talking about as far as the Earth's atmosphere, where we need infrared in Earth's atmosphere. And that's the greenhouse effect, or the natural greenhouse effect. So sunlight is what you're going to be using for UV. Which is really a minor part. It's only about 8% of what comes to us from the sun. The rest of it is visible light, and most of it is heat or infrared that we have from sunlight. So you don't need to worry that much about UV as far as it being just a fraction. Okay, so let's take a look at the next one, which is here. So when you've got UV radiation, this can be broken out into the component parts, just like visible light can be broken out into its component parts. So this is UVA, UVB, and UVC. So UVA, UVB, and UVC. And we don't actually get all the forms of UVA, B, and C. In last week's discussion, we talked about UVC, which is the highest energy. UVC is the highest energy, and for the most part, that is completely absorbed in the atmosphere. And so it's completely absorbed in the stratosphere and it does not reach us. So that does not reach us. And so we don't have to worry about that. And that's good, because if we did, that UVC being the highest energy, that would cause problems as far as long-term and even short-term damage, sunburn, and skin cancer. So UVB, which is the next lowest or medium energy, some UVB is absorbed in the atmosphere or the same stratosphere. And we'll look at those reactions. How UVC and UVB are absorbed is not like a sponge absorbing water. It's through reactions where ozone and oxygen take in the energy in their bonds of the molecules and causing those bonds to break. And so they're basically sacrificing themselves. The molecules are sacrificing their own bonds by taking in UVC and UVB energy. Okay, so some UVB reaches Earth and some does not. Okay, but all UVA, that's the lowest energy, all of that reaches Earth. And that's good. We're lucky that of the ones that what does reach Earth, it's UVA because that is the lowest energy. And UVB, even though it is medium energy, it does have some beneficial effects. So UVB can lead to vitamin D production. And vitamin D we talked about in lecture. Vitamin D is something that your body needs for teeth and bones. And you can take vitamin D as a pill, or you can be outside for about 10 minutes a day, which can be additive. You don't have to do 10 minutes every day over like 3 days, 30 minutes, and then not the other days, but you will get vitamin D for free if you just have your skin exposed to UV, and specifically it's UVB that initiates those reactions. Also, suntan, and suntan is a beneficial effect. It can make you look healthy. It also can prevent the next level, which is sunburn. And so it depends on your skin type, whether you're getting a suntan or a sunburn. So UVB also has damaging effects. So UVB leads to sunburn. And UVA, which is the lowest energy, but it penetrates deeper, UVA leads to long-term skin damage. Okay, so longer-term skin damage like aging, wrinkles, and spots. And who wants those? Now, it doesn't happen immediately. It is a penetration that then affects molecules and cells deep below several layers of the skin. And this is unlike UVB that is really at the surface. So suntan, sunburn, vitamin D protection, that's at the surface layer. That's where UVB reaches. And so both UVA and UVB together, so both UVA and UVB over time lead to skin cancer. So we'll get to exactly how to protect yourself from the skin cancer and other things that are caused by the UV that does reach Earth. So again, this is how the molecules do this. So this is called the Chapman cycle, and this is occurring in the stratosphere. These are the reactions in the stratosphere where UV is absorbing, UV is absorbed. Okay, so this is the absorption. Absorption, I gotta spell that correctly, absorption of UV. So it's not being absorbed like a sponge absorbs water. What you have is UV coming in from the sun, and before it hits Earth, it hits the stratosphere, because the stratosphere is above us. We're in the troposphere. So way up in the stratosphere, above 30,000 feet, this is all happening. And so this is UV when it runs into O2. So O2 is an oxygen gas molecule. So it's an oxygen molecule, and drawing it out, O2 we know is two oxygens bonded together with a double bond. So that's a double bond, two bonds connecting the two oxygens. Okay, and what happens when it's hit by UV is that this bond will break. And so this bond will break, and it breaks this double bond. Okay, and that's the absorption, is UV causes the breakage of that double bond, and then the UV is absorbed because it was taken into that bond. Okay, and this is going to produce two oxygen atoms. And those are oxygen atoms that are very reactive. They have an unpaired electron. Okay, so they're very reactive with an unpaired electron. That's that dot. And that very reactive oxygen will then go on and react with something else. What else is in the stratosphere? Just other oxygens and ozones. Okay, so there's not much in the stratosphere going on, but it will react with whatever else is there. So it'll react with a different oxygen molecule. And there are millions up there. So it'll react with a different oxygen molecule. And then what is produced is this O3. And this is O3 that is ozone. So this is O3 that is ozone. And the structure of ozone is a double bond on one side of essential oxygen and a single bond on the other side of essential oxygen. Okay, and so that ozone molecule structure, so this is ozone that's formed, but we'll also look at how that ozone is also broken down and absorbs UV. This again is going on in the stratosphere. So this is UV here, same thing, we had UV here, and UV will break down oxygen and will also break down ozone. So when UV comes and hits this molecule, it will break this bond. Okay, UV can break this single bond. And the UV energy could also break the double bond. So let me draw this like here. Okay, so now there are two possibilities here. When the UV in the stratosphere hits an oxygen, it breaks the double bond. When UV in the stratosphere hits the ozone, it can break the single bond or the double bond. Now, when you think about breaking a bond, think about this like if you've ever seen in karate, you can break a board, okay? So when you break a board, you just like basically karate, you just take it and you go boom, and just breaks this board, goes, okay? So what do you think takes more energy? Breaking one board, boom, or breaking two boards stacked next to each other? Which one do you think takes more energy? Or in other words, which one takes less energy? So breaking the single bond takes more energy, or breaking the double bond takes more energy? Anyone? Which one do you think takes more energy?
Breaking a double bond?
Breaking a double bond. Thank you, Jackie. Thank you, Alexa. Yes. So this takes more energy. And so there's the molecule of oxygen. Breaking the double bond takes more energy, and breaking the single bond takes less energy. Okay, and so that's where the differential between the UVs come in, is which of the UVs that are up there has more energy. That's the UVC has more energy, and that UVC is absorbed by both oxygen, the O2, or O3 in breaking those double bonds, compared to the slightly less energy, the UVB can only be absorbed by ozone. So this is why some UVB is taken care of and absorbed in the stratosphere, but not all UVB. So this is all UVC is completely taken care of. There's enough oxygen, O2, and enough ozone, O3 in the stratosphere to handle all the UVC, and it all gets absorbed before it can reach Earth. But then because only the remaining ozone molecules, the remaining O3 is available to take care of the UVB, the lower energy, there's not enough ozone to go around to take care of all the UVB also, okay? And so this is the idea, is that all that UVC is completely absorbed before it reaches Earth in these reactions. So this also leads to breakdown of ozone. So ozone is also broken down and returns to the oxygen. And this happens every single day during the daytime. So this is a steady state condition that occurs only during the day when we have sunlight. Okay. And so every single night, all of this goes back to what it was, which is just oxygen. And during the day, ozone is produced, ozone's broken down, but this happens every single day. And this is just a normal production of ozone in the stratosphere. Okay, so we've got the next slide, which is here, which is the UV that does reach Earth is UVA and UVB. And they penetrate the skin to different degrees. So remember, UVA is the lowest energy. And a lower energy means a lower frequency or longer, higher wavelength. So having a longer wavelength compared to UVB, which is a higher energy. Higher energy, remember, is linked to frequency and wavelength. Higher energy is a higher frequency and a shorter wavelength. So the longer wavelength, UVA, can go further down and go into the lower levels and penetrate the skin. So UVA can penetrate several layers of the skin with the longer wavelength. And that's why UVA causes the damage below, the skin aging, the wrinkles and spots, that all happens below the surface, versus UVB is only basically on the surface layers of your skin. And so that's right here. Shorter wavelength, it gets stopped right there. And those are those reactions right at the surface of your skin, the vitamin D production, the suntan, and the sunburn. Okay, so UVA and UVB are what reach Earth, and they have different effects. Okay, so what we do need to protect ourselves from mostly is what happens to the skin. So this is where you use sunscreen and sunblock. And sunscreen and sunblock, they have nanoparticles in these lotions. And these nanoparticles will basically absorb the UV energy, the UVA and UVB. And this is kind of like the same thing that we just looked at. There are molecules, the ozone and oxygen will absorb UV in the stratosphere. Well, these lotions, sunscreen and sunblock, have molecules that absorb UV energy in their bonds. And the bonds are not necessarily broken, but they cause these bonds to kind of vibrate a little bit and absorb energy. Some of them do break, which is why sunscreens do need to be reapplied because they are broken down in the process of absorbing UV. Or sunscreens have an expiration date because these molecules are they're not especially hardy, and so they will break down, not immediately, not like how bread or milk goes bad, but they do break down, and that's the goal, is when exposed to a UV, these bonds will break, and they will be working though. So what distinguishes different sunscreens and sunblocks is the SPF value, and SPF stands for sun protection factor. And the sun protection factor is not a percentage. It is not an amount of time. It's not anything that you might think. What SPF is, it is a factor, and it's a multiplication factor. So you have a base amount of time that is different for each of us. how much time does it take before you will burn? And this is in the absence of wearing sunscreen or sunblock. How much time will it be before you burn? Could be 10 minutes, could be 30 minutes. So you start with that base time. So let's say your time before getting a sunburn is 10 minutes. Okay. So what the SPF factor is that you get to multiply that time that you would burn. So SPF 30 would be, you get to multiply times 30, and that would give you 300 minutes before you burn. And so it gives you more time. Okay, so it allows more time in the sun. So it's not a percentage. It's not more protection. It gives you more time, because all SPFs will protect. But the number value, if it's SPF 5 or 100, that just gives you a factor of time more than your base time of burning. Okay, and so all SPF values protect well. And the reality is that if this is an SPF 30, that's really the most anyone ever needs, because all sunscreens need to be reapplied every 2 hours. And so reapplying every 2 hours, that's every 120 minutes, every 2 hours. And so if you had a base time of burning of 10 minutes and you buy an SPF 30, you get 300 minutes. That's well above the 120 minutes in which you need to reapply it. So that's what I'm talking about, is that you basically don't need to spend a lot of money on those higher SPFs, but you do need to make sure you reapply every 2 hours. Now, I know that I don't always reapply every 2 hours, but if you really are going to pay attention to the instructions on the sunscreen, it has to be reapplied every 2 hours or 120 minutes. And it also has to be applied in a certain concentration. And the concentration is a lot higher. Most of us don't use the proper amount. It's studies show that most people use about 50% of what they should be using for the effectiveness of that sunscreen or sunburn. Or for the effectiveness of that sunscreen or sunblock. Okay, so, but what SPF allows is more time. Okay, but there are other ways to protect yourselves. So you can just stay in the shade, and you will see in these experiments today that there's still UV in the shade. There's less, but you still have UV, because UV can reflect off surfaces, and we can't see that UV reflecting off surfaces. You can also just wear clothing. So clothing, and you'll see I will be testing fabric. Clothing is a layer which is very similar to sunblock, which is supposed to be like a physical layer. That will just basically block out any sun from getting in. That's the same as a hat. And sunscreen, sunblock, this actually recommends a protection of a minimum of SPF 15. So 15, 30, that's actually all the SPF anyone needs. You really don't need 80, 100, but you do need to make sure that let me go back to that. I need to make sure I go back to that. You do need to make sure that if you are buying a sunscreen, it should say UVA and UVB protection. This is also called broad spectrum. And that's important, because this is what reaches Earth, is UVA and UVB. And that's what broad spectrum means. It's the spectrum of wavelengths that include UVA and UVB. And so you should look at your sunscreen and see, does it say broad spectrum or UVA, UVB protection on it? Okay. And if it doesn't, then you should start thinking, well, is this going to work? And that's why you can test it. So going back to here is that you should make sure that you should have a sunscreen or sunblock should be a certain SPF, and have UVA and UVB protection. And then what about sunglasses? Well, sunglasses are super important, because you can't put sunscreen on your eyes or sunblock on your eyes, and UV does bounce off. And so this is really important when you're in the water or sand where UV-like light, this bounces off surfaces and it bounces off into your eyes. Now, you can't get a sunburn in your eyes, but UV in the long term leads to cataracts. And so that's decades away for most of you, maybe even me, but that long-term exposure, continued exposure of your eyes to UVA and UVB will lead to cataracts. And that's why most people do end up having to get cataract surgery. But you can prolong that by wearing sunglasses, and they need to be proper sunglasses. So what are the options that you have for sunglasses? Well, there's colored lenses. So what do colored lenses do? Not much. So if you've ever had some cheap sunglasses and you put them on and you notice, oh, everything looks a little pink or everything looks a little yellow. What colored lenses do is they just filter out one color, okay? And they're not filtering out any UV. How about mirrored lenses? What do mirrored lenses do? Mirrored lenses, they also don't do much. They look cool. They reflect light off the surface, and that's about it. So they do not protect from UV. What about polarized lenses? So this is what polarized lenses do, is that they filter out wavelengths of the other wavelengths, reducing glare as a result. So it only allows in certain wavelengths and you only see like a clearer picture. So that's glare that's filtered out. And polarized lenses, which are pretty expensive, they are important if you need to do precise things outdoors, like driving. And so you don't want to have glare when you are really needing to see something clearly outside. But what will protect your eyes from UV is this designation called UV 400. And let me actually put this on my screen here, is the sunglasses generally should have a designation showing that they are protecting against UV. Now, unlike sunscreens and sunblocks that say UVA, UVB protection, this has a sticker that shows UV 400. And what that means is it protects in the UV wavelengths. And so that's what and these are not even expensive sunglasses. These were actually cheap sunglasses too, but having a sticker on there saying that it protects, that has 100% UV protection, that's what's going to be important when you're looking for sunglasses. So if you're thinking, well, I don't know if my sunglasses protect from UV, then that's what you're going to want to test your own sunglasses and see if they protect from UV energy. Okay. So the UV index is another way to protect yourselves from UV. Now, where can you find this UV index? Some different places. So the UV index is something you can use just like using the weather daily or the air quality report daily. It's something that changes daily. It depends on your location by zip code. You can look up the UV index. It changes based on the day, the weather. For instance, like a cloudy day will affect UV, or a rainy day. And then it also changes hourly when the sun is out or the sun is brighter, or seasons when you have a longer day. So this also you have on an iPhone. This is the weather app. On the weather app, you have the air quality, you have the weather, and you also have the UV index. And the UV index is linked to these number values. And so these number values are colors, but they are more importantly linked to protection advisories. So here's the suggestions for protection advisories. And so this is the protection advisory, and you will need this. For today's lab, you're asked to basically report the protection advisory for a day like today. And so the index number value, if you have anything in this range, so 0, 1, or 2, burn easily. If you burn easily, cover up and use sunscreen. So sunscreen is at the base level, but this continues on to moderate, high, very high, and extreme. And what they have in common as the UV intensity increases is that basically you want to pay attention to these hours between 10 and 4. If you want to protect yourself, you're either going to reduce exposure, minimize exposure, or avoid it altogether. And the hours of highest intensity UV are between 10 a.m. and 4 p.m. Okay, so let's take a look at today's lab. So I'm going to here